Hello, my name is Matthew Maher from Processus Group. In this session for TechNet, I'll be briefing you on our paper, Reducing the Warfighter's Cognitive Burden Through AI and ML. In the paper, we outline a detailed approach for how we align cognitive capabilities with operational processes through the use of knowledge graphs. We use these knowledge graphs in the AI and ML learning process. This process will help DoD have a higher success rate in implementing AI. What we'll discuss in this session is why is AI failing across DoD? How do we align the learning process of AI and ML to the operational processes that the warfighters execute? How do we align data to the functional model, the learning process through knowledge graphs? Our paper goes into greater detail, so we'll give you a summary of what the paper outlines. So the first thing we have to look at is AI is not a plug and play solution. It's been briefed that only 14% of AI developments across DoD have been successful. That means we're sitting on about an 86% failure rate. Why is that? Well, the simple answer or the fast answer is it's going to be the data. But when we say data, what do we mean by that? As a data scientist and with my operational experience as a former Army officer, I work mostly in SOCOM with their Special Forces Group and other SOCOM type units. Across DoD, we have a problem with the 3 V's, the volume, velocity, and variety of data, and how that's applied to the learning process. But even that is too generic an answer. We have to address data and AI capabilities with the operational process. Is what we're trying to ask the AI or machine learning to do, is it really going to reduce the warfighter's cognitive burden? Is it going to help them execute their day-to-day jobs? By building functional models that define the operational process in both the machine and human readable format, we're able to explain where AI can be implemented, what decisions it's making, and how it makes that decision. We create the knowledge graphs that align the data to the .mil PFP structure. This way we can look at how doctrine plays in versus training versus material versus policy versus personnel. We can start to link all of that together in a knowledge and experience of the warfighter's mission. Our paper, Reducing the Warfighter's Cognitive Burden, actually won an award from the International Conference for Cognitive Computing for showing how we treat human knowledge as a part of the model. So for example, the way we treat data being created from a material solution or from a system is the same way we treat the training and understanding from the personnel side. So you get that extra layer of a pattern capability and the mathematics underlying it on that solution set. So that's why it's important that we make these models machine and human readable, because we want the validation from the warfighters also. We reduce the warfighter's cognitive burden by building the knowledge graphs that help train the AI and ML capabilities. And they respond to the way a soldier, Marine, Seaman, or Amrin would execute their day-to-day functions. So when we talk about knowledge graphs, how does that apply across the enterprise? Well, across the domains in DoD and where we're trying to implement AI solutions, we're facing a lot of data silos. We've known this problem for several years, but we really haven't gotten better at how we actually implement data. So when we start looking at, for example, the decision-making process or the planning process, we have to look at data coming in from the intel side, from the fires, from maneuver, looking how all that applies to, let's say, commander's intent. We'll show you in some of the models that we developed on how we actually address that, how we actually capture the concept of commander's intent for when we're looking at terrain analysis or for the planning process. Or from transitioning from offense to defense. All of our knowledge graphs are based on doctrine. Every single one of them, we have about 86 knowledge graphs right now across operational processes that have all been validated, from the Fire Center to the Intel Center to the Cyber Center, and SOCOM and the Marine Corps. The Marine Corps and SOCOM are the 2 most recent ones that we did, so we'll show you some of the successes we've had. This is not theoretical, we've actually implemented these. When we've done the work recently with the Marine Corps and SOCOM, we've realized that some of the benefits we get from doing the knowledge graphs up front is we reduce the AI planning times, reduce the AI preparations time. We essentially build the left and right limits of what the model needs to do. And we'll discuss our 3-step process for cognitive architecture, semantic data models that turn into knowledge graphs, on how we can start to show where the AI needs to be implemented, where the cognitive burdens are, how the data applies to that, and how we break that up. So the models, again, define those left and right limits, or basically the playing field of what the AI has to learn from and how data applies to all those concepts. We get faster decision making and development of the functional models. We can actually look and understand what the models are doing. We'll discuss that a little bit more in the next slide. And above all, we reduce the warfighter's cognitive burden because we're able to show where we can actually implement AI or where somebody's having a struggle because too much data is coming in for the human to be capable of actually processing it. So we mentioned the explainability. So along with data, even if you have your data perfect, when we're talking about DoD and the AI or machine learning algorithms spit out the functional model, and then we run through it again, it's impossible to understand the deltas between the first run and the second run because the models are created by a system or a computer. They're not explainable. Basing everything on a knowledge graph, which has a mathematical foundation, and then running it through an AI algorithm, we can start to see what the deltas are between the base model and the learning pattern. Because what the knowledge graph actually does is it creates a lot of those patterns up front. We use several mathematical algorithms or some algorithms that actually work to mathematically show how the knowledge graph is laid out. We'll create the nearest neighbor, the centrality matrix, the adjacency matrix to show how classes and data are aligned and what the relationship is, how close they are to each other. And we'll show you an example of that. Based on this explainability, we have a better understanding of what the AI, the learning process is actually achieving. So we're able to make sure that that is more accurate. And along with the data, we're cleaning the data as we're building that out. The knowledge graphs, when used right, help with decision flows, can be used for more transparency in the AI decision-making process. We'll jump into the model now to show you some examples of how this actually looks to give you a better understanding of what the models actually do. So what you see here is one of our very basic models. This is a much larger model, but we wanted to make sure it's readable for the group. So what you can see here is some of the structure of the .mil-PF. We have organization, we have personnel. This is one of the Marine Corps models. So we started to look at what are the organizational processes that are executed, what are the functions that are within those processes. We want to look at the ground combat element for ground reconnaissance, defensive operations, offensive operations. We want to look at how the function of command and control applies to these and what the role of the commander is, the commander's intent. So this is a very simplistic model, but you can see we start to show the relationships here, how things come across. One of the areas that we were discussing in one of the AI capabilities that we were briefed on, we weren't part of, one of the issues was the AI algorithms had a trouble from distinguishing between a commander and a command post. As you can see with our model, we can clearly show that a commander is part of personnel, where a command post, even though it's not on this, would show up as an organizational structure that belongs to someone in that organization, whether it be a brigade, battalion, regiment, and then it has material assigned to it. So there's a way to define what the classes, what the data means, so you don't have that confusion. Now I'll show you what this looks like in a little bit more detail. So here what we have is really the knowledge base of what we're looking at for the commander. We have the commander highlighted here, and we're looking at all the relationships that the commander has in that current model situation. So one of the things we talked about is within command and control, the commander has certain areas he has to look at within his commander's intent. So these are the knowledge base that we want to start looking at. These are hard to read, so I'll read some of them out. But basically, the commander has to be flexible according to doctrine, has to act quickly, has to provide for the security of the force, maintain momentum, influence the plans to accomplish the mission. So all these are knowledge-based concepts that we're able to capture. And as we interview the warfighter and discuss with these, we start to align what data actually applies to that. So we can start to map in plan for security of the force. We can start to show that there's terrain data that's important for that. There's fires data that's important for that. Obviously, there's enemy data that's important for that. We start to map all those data elements to this knowledge base. We start to learn, and then we understand from the warfighter what that knowledge base means. So what would make you turn left versus right, and we can capture that in the model. And I want to talk to you about the mathematical base. So as we start to look at the relationships, you can see that these are starting to grow. There's algorithms that are being applied that show, again, this is the cluster effect, to see how things are clustered together, where they relate to each other, and they're starting to separate to show how mathematically you can see some are closer, some are further away. That's the algorithm saying that there's more relationships between the ones that are closer and less relationships with the ones that are further away. As we get back to the brief now, we want to show what does the knowledge graph provide for you? In the paper, we outline 3 key areas, which we'll get onto the next slide. But from a larger side, we want to look at what does the knowledge graph actually show you. So one thing we show based on .mil-PFP structure is it shows how you fit into the big picture. So as we start to look at where we want to implement AI or machine learning or any of the other cognitive capabilities, you can start to see how does that actually apply towards the larger operational concept. What are we trying to do it for? With the knowledge graphs, we're able to capture data plus knowledge, as we described before. But data plus knowledge equals an understanding that's beyond the level of what we can actually achieve through the normal functional models. We can start to understand how the decisions were made, has it more accurate, and correct those in a more timely fashion, as opposed to what we do in normal AI, where we just push more data through and eventually start to get to the area where we think we're close enough to the right. Are we doing the right things? Are we implementing AI in the right areas? Are we basing it on the concept of how we help the operation process? Since we start with the knowledge graph, we have a mathematical starting point. We can create both in a machine and human readable format. So we can get that validation before we even start the training process that we're on the right path. What I like to say is when we build the knowledge graphs, we build what right should look like. This is based on doctrine, it's based on the material, it's based on warfighter experience, the training. So we build those models to show what right looks like. Anybody that's involved with data, they realize data is a reality. It's never the right picture, but the data will show the reality. There's anomalies, there's errors, there's omissions, but we have to live with that. But understanding mathematically what right looks like and mathematically understanding what reality looks like, you can see that we can then figure out what the delta is between the two and help with that learning process. We build these so we can show the cause and effect relationships. Again, that goes back to the warfighter knowledge. Why did X become Y? Why did we turn right based on these enemy actions? And again, we get to break down the data silos. We get to understand how the different data points tie to each other. So for example, if we're looking at the fires process, there's certain documents that are produced for that, the attack guidance matrix. We understand how intel data comes in to identify which of the targets are applied to that. Then we look at the fires data and the weapons data and even the EW or cyber to look at how we'd actually attack that target. What would be the weapon system that would go against it? What is the effects we want? All that gets combined, so we start to see where the data needs to come from to come to that solution on how we actually commit an AI solution for fires and breaking down those silos. Knowledge graphs help us to apply the learning process to overcome the volume, variety, and velocity, because we look at all of those as a holistic standpoint within machine learning concept. So I keep mentioning this. In our paper, we talk about three key areas: cognitive architectures, semantic data models, and knowledge graphs. All these are really one big knowledge graph, but we start with the cognitive architecture. We like to start with the organizational structure within the .mil-PF and the doctrine. What are they trying to achieve? We build that big picture that combines the concept of, we call it DICOE. It's data, information, knowledge, understanding, and intelligence. How does all of that apply together? And we start to build that out where we can start to use, again, the mathematics that you saw before to see where there's clusters, where there might be an overburdened warfighter based on data or based on processes. As we break that down, then we get lower level and actually start looking at the data. That's where the semantic data model comes out. What's nice about the semantic data model in this graph structure is you're able to combine the actual data elements with the metadata or the meaning of the data. In most databases, you lose that connection because the metadata and the data are not stored together. In a graph structure, they're always together. The metadata is actually more important than the data, or the meaning of the data is more important. So you always have those combined. And again, I keep mentioning that's machine readable and human readable, which is important because, again, we can show from a program perspective that you're on the right track, or from an operational perspective that we're building the right thing. And then with it being machine readable, we're able to make sure that it has an understanding of what that data means. And then the final output is the knowledge graph, which defines the levels of how we actually execute this. It builds that base structure and it shows how all of these three pieces come together. And again, we are able to address the three V's by looking at the volume of data with the cognitive architecture, where's it coming from? And then the semantic data model starts to explain that, and knowledge graph gives a picture of how it all ties together. So with the volume of data and the cognitive architecture, we really define the how and the where data is leveraged. We start to look at the key information, the DICOE, the relationship between that. Where's the data created? Who needs to see it? How is it sent from A to B? We start to look at that. We answer three core questions here. Where are we creating the data? Does the data need to be stored? And how does this support the decision-making process? Once we complete the cognitive architecture with the semantic data model, we start to answer the what and the why. And again, this is a much lower level data model. It's actually a data model on steroids, if you think of it that way, that actually shows how the meaning of data and the operational process align to each other. So in this one, we start to create, though, what types of data are being created? What is the correlation of data that needs to be accessed based on type and format? Meaning, if it's coming from the different data silos, how do we correlate that? What is the meaning? If I have the same term, but it means something different between Intel, Fires, or Cyber, we can make sure we add that to the model so we understand that what the data element means based on the different silos it comes from, and how systems can access the data smarter. We create a semantic data layer that actually allows us to overlay a traditional database. So when a system's accessing the data, they actually have that graph structure on top of it, or semantic structure on top of it, that shows the meaning of data, or it allows it to access the meaning of data. The next is the velocity, which is the actual knowledge graph. How much of it's coming in, where it's coming from. We answer the when and the who. When will it be created? Who needs to see it? And through this, we're able to increase the speed of data being created, understand where it's coming from, how it's being accessed, the speed of analytics needed, where the decision-making process has to happen. Is it closer to the collection or closer to where the data is being created? And this is how we start to address the 3 V's. The paper goes into much more detail of how this works and what the products look like, which I'll show you on the next slide. So here we have the .mil-PF knowledge graph. This is the ones we stuck for SEMA optimization. What you see on the left-hand side there is our large operational process picture, how everything ties together. We then extract certain operational concepts. What is the planning process? What is the execution piece going in QOps? We tie that to the data structure. What are they doing? How does that align to operational tasks? We start applying the mathematics and the data science to the models, and then we apply that to the ConOps. So then we can start to look at, all right, if we wanted to just build an AI solution set that was just for the commander's intent, which I showed you before, we take a subset of that model to the left and start to build that out and show what the relationships would look like. What's also nice about a knowledge graph is you can think of it as, it's also a data fabric. The reason why I call it data fabric, if you think of it as a blanket on a beach. If I pick it up from the right corner, it takes a certain shape. If I pick it up from the center, it takes a different shape, but it's still a blanket. From this model, we can look at it from any perspective. We can look at it from a personnel perspective out, or from a doctrine perspective in, from a material solution. And all the relationships show based on the way we're looking at the model. So this is how we can apply the operational concept to this. So in summary, we talked about the why, the how, the what, and the results. So let me try to paint the picture a little bit more. So why do we use knowledge graphs? Because we really combine that data with knowledge, and we're able to show that across the operation process. We're able to show what right looks like. And again, it's mathematically based. Our tagline, data plus knowledge equals understanding. We have that operational process outlined, what data is created, who needs to consume it, when they need to consume it, and what should be the results of that consumption, meaning a buyer's or an Intel product. How we do this, we explain a little bit more detail in the paper, but hopefully you understand the concept of how we apply .mil-PF across a cognitive architecture, the semantic data model in the knowledge graph. The knowledge graphs create a dynamic knowledge base. They're able to query it, you're able to look at it, you're able to read it to see what is actually being applied across it. You can see from the picture to the right, what we talk about with the .mil-PF piece is we understand the mathematical right of what it should look like based on doctrine and experience. When we look at the raw data, we have a mathematical representation from the analysis of what reality is. Once we start to understand what right versus reality is, then we can start to train our AI solution sets much faster and much more reliably. We believe we know doing this up front that you will reduce the risk on any AI capability because you'll have a better understanding of where you want the AI applied, what the state of the data is, what the data is being applied for. The results speak for themselves, and we're able to provide you that. In summary, we've used this across multiple entities, and it's always worked for us. It's a much better approach when we start with this process as opposed to just jumping directly into AI. We're hoping to get that 14% success rate to be significantly higher. We need this capability out for the warfighters, and we need to do it right. Again, my name is Matthew Maher. If you have any questions, my email is below. I also have my partner's email on there, Rob Orlando. Please reach out to us, and thank you for your time.